and talk about what does this distance represent. So this distance is called a coupling constant. So in my quartet, the distances between all four of these peaks are equal. So the coupling constant can be measured between any two adjacent peaks. So even though our x-axis is in ppm, we're going to measure our coupling constant, which is called J for some weird reason. We're going to measure it in hertz. Why is that? Well, it turns out that depending on how good your magnet is, how big your magnet is, those peaks are going to be closer together or farther apart in ppm, but it's not going to affect their actual resonant frequency in hertz. So this is a conversion that we have to do. It's a really easy conversion. So all we need to do is take the difference in ppm and multiply it by our NMR frequency. So that's going to depend on what magnet that you use. Here at Lawrence, our NMR is a 400 megahertz instrument. And so whatever distance we measure between the peaks in ppm, we multiply by 400, and that is our NMR, that is our coupling constant. So for instance, let's say that this quartet here, these last two peaks are at 1.32 and 1.30 parts per million. So to find the coupling constant, we would take the difference between those two, that's 0.02 ppm. We'd multiply it by our field strength of the magnet, which is 400 megahertz. So the coupling constant of this quartet, we would say, is 8 hertz. So coupling can be big or small. What dictates coupling? Coupling depends on two different factors. The first factor is simply how close the atoms are to each other. In particular, we can talk about the number of bonds that separate these unequivalent protons. As a reminder, if protons are equivalent, if they're the same by symmetry or because they rotate fast, we're not going to see any coupling there, right? So these two, we wouldn't say, oh, this one's got two neighbors. No, because they're the same, they would not be coupling each other because there's a line of symmetry down the middle. Most bond coupling is 2 or 3 bonds. Most of it's actually 3 bonds, right? So we drew this before. 1, 2, 3 bonds separating those protons. Once in a while we can see 2 bonds, which would be on the same carbon if they are not identical. And we'll talk about when they wouldn't be identical later on. In some cases you might see 4 bond coupling, particularly on benzene rings, but that's pretty uncommon and it'll be a really small number. So the other thing that it depends on is the dihedral angle. So remember we talked about the good old butane and rotating like this, right? That's the dihedral angle we're talking about. It turns out that because we're talking about bar magnets, maybe this isn't surprising, it has the biggest sort of communication effect when the two are aligned, either 0 degrees or 180 degrees. Right? And so there's something called the Karplus equation, discovered by Martin Karplus, where the dihedral angle is greatest at 180, it's pretty big at 0, and it's nothing at 90 degrees. That's the Karplus equation. Martin Karplus won the Nobel Prize for something completely different. This is one of the most important things in chemistry, and Karplus won the Nobel Prize for something that has nothing to do with this. I'm amazed by that. Anyways, so these are the two things that dictate whether coupling is big or small. How close two atoms are together and what the dihedral angle between them is. What do coupling constants look like? So the most common coupling constants you'll see, especially the biggest and the easiest to pick out, are these. When you've got a normal alkane or just carb, how big are coupling constants usually? So all of these are example of 3-bond coupling or vicinal coupling. Vicinal like neighbors, like I live in the vicinity, that kind of vicinal. So here typically vicinal coupling is 6 to 8 hertz in alkanes, most single bonds. For double bonds, it's a little bit bigger because these atoms are more or less frozen into a good dihedral. So for a benzene ring, two things next to each other in a benzene ring, that's called an ortho relationship. So I forget if we've used that word before, but we're using it now if we haven't. So ortho, neighboring protons on a benzene ring. The word ortho is not used if we are not talking about benzene, only benzene. But here, these two have an ortho relationship, and they're going to see a coupling constant of 8 to 9 hertz. Alkenes have a little bit higher coupling, so a cis alkene would be 10 to 12. A trans alkene would have about the biggest proton-proton coupling at 14 to 18 hertz. You are not going to see any coupling above 18, 20 hertz. If you see coupling above 20 hertz, you've either done your math wrong or you're looking at two peaks that are not actually coupled, that just happen to be kind of close together. Sometimes we see geminal coupling when two hydrogens on the same carbon are not equivalent, and we'll talk about when that might be in a little bit. But on the end of an alkene, that's sometimes common. We'll see a very, very small communication there, about 1.3 hertz. In general, in other cases where two hydrogens are different but on the same carbon, the coupling constant varies quite a bit. One more important type of coupling is what's called meta. So again, I don't think I've used these words, so here we go. Meta is the relationship where it's sort of two down on a benzene ring. So I would say these two protons are ortho to each other. These two protons are meta to each other. It's a relationship word. These two protons are trans to each other. These two protons are meta to each other. Again, ortho and meta only have context on a benzene ring. Okay, so here, even though there is 1, 2, 3, 4 protons, or 4 bonds separating those two protons, there's still a weak coupling constant there, partially because they're held planar, and so they're a little bit easier to align when they're stuck planar like that. But we will see ortho coupling is quite a bit bigger, they're closer together, but there still might see some meta there as well. You might say, what's the relationship when they are across the ring? Across the ring is called para, and there's no coupling because they're too far away. So 3 relationship words when it comes to the benzene ring. Ortho is next door, meta is Latin for 2 doors down, maybe, and para is across, right? Para, I think, is Latin for across. So para, no coupling there. Okay, this is amino-salicylic acid, 4-amino-salicylic acid, derivative of aspirin, I guess. So here I've got the chemical shifts for these 3 ring protons down here. When I take the NMR of this molecule, it looks like this. There's a big doublet here, there's a little doublet here, and it looks to me like 2 doublets, or almost a doublet of doublets there. So why is this? And we'll talk about why this is at 7 and these are at 6 later on. It has to do with this being a withdrawing group and these two pushing electrons into the ring with their lone pair. But what's going on here? What's going on is that this proton has 1 ortho coupling. So I'll put an O there. Okay? And so it's got 1 big coupling constant there. This one over here, this one has 1 meta coupling constant there. And so that's this one, right? So here I only have the 1 meta coupling, whereas here I have the ortho coupling. And remember, ortho coupling is over twice the size, right? This is 8 to 9, this is 1 to 3. Okay, so what's the deal here? Well, look, this hydrogen is split by 2 different protons by different amounts, right? So now my little diagram looks like 1 big coupling constant and 1 little coupling constant. So what I'm going to get is a doublet of doublets. We call a DD, where this distance between 1 and 3 is the same distance as that, but the distance between this little distance is the same as this little distance. Okay, so this is a common thing that we see in aromatic rings, where we see ortho coupling, right? Neighboring protons coupled pretty strongly to each other, but protons that are meta to each other couple much more weakly. And sometimes we see these doublets of doublets. Here's another example through the magic of picture-in-picture. So here is an alkene with 3 alkene protons, right? So we can actually tell the difference between these three. They're all kind of complicated multiplets being a general term, but they're not that hard, right? So if I look at that red proton, the red proton has a cis partner and it has a trans partner, right? It's cis to the blue proton, it's trans to that black proton on top. And so it's going to have two coupling constants, one that's kind of big, 10 hertz, and one that's pretty big, 17 hertz. And so we're going to see a doublet of doublets. So again, the distance between the first two peaks there is that shorter coupling constant, and the distance between like the first and the third peak is the bigger coupling constant. If we look at the blue peaks on the far right side, now that blue proton has a cis partner, the red one, and a geminal partner, the black one. And so we see a teeny tiny coupling constant, that's the geminal coupling, and then we see a medium coupling constant for the cis coupling. Then finally, between them is that black proton. It's got one big coupling constant because it has a trans partner, and it has one teeny tiny, can barely see it, little flare of a coupling constant because it has a geminal partner. Okay, so those two on the right side look more like doublets at first glance, but if you look really, really carefully, there's that really, really fine splitting, and that is a weak coupling from the two geminal protons on the end. If you notice that there's none of that fine splitting on the red proton to the left. So again, these are multiplets, doublets of doublets, because they are split by two protons unequally. So once again, 3 pieces of information for every NMR peak. First, chemical shift, how electron rich or poor it is, how shielded is it. 2, integration, how many there are, very clearly, how many in relation to other peaks. And then 3, splitting, how many neighboring protons does that proton have. With these pieces, we can really put the puzzle of structure determination together. And now that we have them, we'll spend a lot of time this week just kind of going through spectra and seeing what we can figure out.